Hello, I'm Purya and today we're diving into the thrilling world of speed. Okay, but how does that relate to mathematics? Let's kick things off by talking about speed. We know average speed is the total distance traveled divided by the total time taken. Now, when we're driving, the speed displayed on our speedometer is what we call instantaneous speed. Let's check the relation between average speed and instantaneous speed. To truly grasp this, let's run a little experiment. For the sake of simplicity and easy visualization, we'll be working with scaled down values. You can assume that the distance and speed we're discussing are divided by 10. This will help us focus on the core concepts without getting lost in the numbers. There is a car here. You can see the information on the right side. When the car starts to move, it's displayed the average speed in time intervals. We'll measure our car's average speed as we reduce the time interval to almost nothing, getting closer and closer to the instantaneous moment. Notice how, as we reduce the time interval, our average speed becomes a closer approximation to the instantaneous speed we see on our car's dashboard. So, how can we mathematically represent this? To make this rigorous in the language of mathematics, we have the concept of limits. We take the limit of the average speed formula as the time interval approaches zero. This limit operation is what bridges the gap between average and instantaneous speed, giving us the power to calculate speed at any given instant. We can express in this way. Yes, the derivatives appear. As we know, the relationship between position and time is a function. Let's denote this function as f. So the last expression is changed to the form what we refer to as the derivative of f. By changing the variables, we can reach the more common representation of derivative we often encounter. We call it f prime of x. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. Thus far, we've determined that speed or velocity is the derivative of the position function with respect to time. Let's consider function f and its associated graphs. To illustrate the concept, we select 2 points along the curve. One point is A, represented as x and f of x, while the other point is B, located at a horizontal distance h from point A. When we aim to find the derivative of f at point x, we calculate the following limit. Note that the fraction we calculate the limit of that is the slope of the secant line connecting these 2 points A and B. As we gradually approach h to 0, point B moves closer and closer to point A, and the secant line approaches what we call a tangent line. Consequently, the slope of this tangent line is defined as the derivative of the function f. Indeed, the tangent line to a function's plot at a given point is a straight line passing through that point with a slope equal to derivative of the function at that specific point. We've established that the derivative offers insight into the instantaneous rate of change at every point along the function. As a result, it grants us the ability to determine the slope of the tangent line at any given point along the curve of a function. Now we can find the derivatives of functions by using its definition. How does it work? In our upcoming video, we'll thoroughly explore this method and unveil derivative rules that provide a more efficient, streamlined approach, reducing the need for extensive algebraic calculations. Dear guys, through our journey we've dived deep into a realm of derivative definitions and tangent lines, unraveling their connection by examining the intricate relationship between average and instantaneous speed. We hope you've enjoyed this exploration, and we look forward to sharing more mathematical and scientific wonders with you in our upcoming videos. Stay curious.